Thank you for reminding me. Okay, we're recording. So we got the 8.2 lesson, area between two curves. So first off, let's just do some very simple coordinate geometry. So what's the distance between 2 points on a horizontal line? Like, see how we have a horizontal line right here? And you have points A and B. So you simply just subtract the x coordinates from each other, right? Like this, we're like, -3, and this, we're at 5. What's the length of that line? Obviously, that length is 8, right? Or just think about just x right minus x left. X right minus x left. Or actually, let me just write that out so it's not confusing. So x right minus x left. Okay. You can see it's kind of worked out off to the right here. So you might remember the distance formula, which is that wacky formula right there. Again, if you plug in the x coordinates, take the difference, square it. The y coordinates, they're identical, so they go away. And so essentially, it's just going to be the absolute value of x right minus x left, or just x right minus x left. Between two vertical lines, like over here, it looks like that length is 4 from A to B. That's going to be y upper minus y lower. Okay, so simple stuff. And we're going to be using this often today, this just simple coordinate geometry. Now, to find the area between two curves in the figure below, so let's look at the figure below now. We partition the region into vertical strips of equal width, delta x. So here we have two curves. We have f of x, and we have g of x. And we want to find the area between those two curves. This is what this whole section is about. So if I partition the region into vertical strips of equal width, delta x, each rectangle has the following area. Whatever y value is here, minus whatever y value is there. For example, what if this were like 2, 8? And what if this dot here was, I don't know, 2, -1? What's the height of this rectangle? 9, right? What's the width of the rectangle? Delta x. We'll call it delta x. So the area is simple. It's just the difference in the y coordinates between the top of the curve here and the bottom of that curve, because that's the height of the rectangle. And how you draw in the rectangles, it could be a left LRAM, RRAM. Don't worry about that. Remember, it's a Riemann sum, so you have pull from how you want to assign that. Times delta x, width of the interval or subinterval. So the area of the region, therefore, is a Riemann sum. It's when you add up all those rectangles. So this right here is the total area of all rectangles. And so we can give the actual area as a limit, and we do as a limit, that's a definite integral from A to B of your top function, which is f of x, minus your bottom function, which is g of x. So that right there is the whole essence of this section. And it's pretty easy. It's actually not a hard section. It's actually, I think, it's good. We end the course with an easy section. So the area between two curves, again, is simply this. The integral from A to B of f of x minus g of x times dx. Very important, f of x is going to be the top curve. G of x is going to be the bottom curve. Now let's do an example. So here we're going to ask to find the area of the region between y equals secant x squared and y equals sine x from 0 to pi over 4. So I strongly suggest to use your TI-84 or Desmos just to get a sketch. Now, I teach this stuff, so I should know how this stuff looks. And actually, let's color code. I will do secant x in red. I'll do sine x in blue. So let's do sine x, because that's easy. You're going to 0 to pi over 4. So sine of 0 is 0. And sine of pi over 4, if this is 1, sine of pi over 4 is root 2 over 2, so it's going to be right here. So if you guys forgot, sine of pi over 4, that's 45 degrees, is root 2 over 2. That's using a 45, 45, 90 triangle bit. Okay, we have that. Now, secant squared. Secant squared is a little tricky. That's where I think calculus would be smart. Remember, secant squared is 1 over cosine squared x, or 1 over cosine x and squared. If you plug in 0, cosine of 0 is 1. 1 over 1 is 1. 1 squared is 1. So you have a dot right here. Cosine of pi over 4 is root 2 over 2. But you got to flip it, so it's 2 over root 2. And you got to square it, so it's 4 over 2 over 2. So it's a little higher. So it looks kind of like this. In fact, actually, if you remember, secant looks like that. But if this is squared, I think they all look like this. Anyway. So I want to find this area. I'll shade it in yellow. We can use calculus to find that area. Why does this matter? Why do we care about this? This is the part that just frustrates me, is that I really want to cover 8.3 with you guys after this. This sets the tone for 8.3. Actually, I think what I might do in the AP study groups, the more I think about it now, I might reverse the order, and maybe I'll do 8.3 next week, just because it's fresh. I don't know. I need to have the weekend to think how because then you kind of see why this is important. Because 8.3 is a really cool section where you start learning how to create three-dimensional shapes using calculus. And this kind of sets the foundation for it. So it kind of stinks that I can't cover 8.3, but it is what it is. So anyway, so that's what we want to try to find. So, and again, just as a little note here, always sketches curves and shade the area. That way you can just to help visualize, right? To help visualize this problem. Visuals are always good. Okay, so which curve is higher? Obviously the secant squared, the one that we did in red. Obviously secant squared x is higher. So now let's do the integral. The integral is really easy. You're integrating from 0 to pi over 4. We'll put a bracket here. Secant squared x minus sine x dx. Now you should know these antiderivatives. The antiderivative of secant squared is tan x. The antiderivative of sine is negative cosine, so it's minus negative cosine x. And you're plugging 0 and pi over 4. And usually we use this this bracket notation to show that you've done the antiderivative, now you're ready to plug stuff in. And that becomes a positive. So now you just do tan of pi over 4 plus cos of pi over 4 minus tan of 0 plus cos 0. Well, what's tan of pi over 4? That's going to be 1. Cosine of pi over 4 is root 2 over 2. Minus tan of 0, which is 0. Cosine of 0 is 1. So final answer, root 2 over 2. That is the area of this yellow region. And you could actually do this in the calculator too if you like. You could just do the fn thing. You go alpha window, test it out. You could do that too. So questions? Nope, okay. And remember, we're going from 0 to power 4, so I had to use those as my limits of integration. Okay. And another thing to think about too is that the other thing that is happening, going back to these curves again, is that essentially you have this right here is shading, right? I mean, that is the integral between that and the x-axis. Then you have all this right here. That's an orange. That's when you look at the area between that and the x-axis as well. But you got to subtract these two areas from each other to really just get that right there. So that's why we subtract also, if that makes sense. But I think this visual also helps that we have all these rectangles that you're generating, that the heights of rectangles are different in the y coordinates between those two functions. That's why you subtract those two functions from each other and integrate it. And we know that the limit of Riemann sum as n approaches infinity is a definite integral. Okay, let's look at another one here, example 2. In example 2, you got intersecting curves. Let's go ahead and graph them first. So let me do this one in red and this one in blue. Okay. So and y equals negative x. So I was going to do it in red, didn't I? Let's do that again. All right, one more time. And negative x. Okay, not the best looking line, but you get the point. Okay, and I want to find this region. So you're asked to find the area between the two curves. So what this means is that we need the points of intersection. To do this problem. It's not hard, actually. The graph helps a lot. I suspect the points of intersection are going to be negative 2 and 1, but to be sure, just set the equations equal to each other and to solve. It's really not too bad. This minus 2. Yikes. Go back. Wait. Did I make a mistake? Oh, I did make a mistake. Someone's correcting me. Mr. You're an idiot. Yeah, I graphed the wrong line. Awesome. But see, I caught myself. How did I catch myself when I found the points of intersection? Because it didn't make sense anymore. Because I should be crossing at 2 and negative 1. So that's my fault. My apologies. Let's take 2. I'm going to blame sleep deprivation. I've been getting up early every day just to, get stuff done for this class and my other classes. So Look forward to getting some sleep this weekend. Okay, here we go. My apologies. That sounds about right. That looks right to me. Okay, if you didn't quite catch that, please make a correction. My apologies there. Okay, now that's why we have all these safety nets, right? We catch our mistakes when we do the algebra. Figure, oh, dude, like supposed to be -1 and 2. So I'm integrating from -1 to 2 of my top curve. My top curve is going to be the red. The bottom curve is going to be the blue. So it's going to be 2 minus x squared minus x dx. Integrate that carefully. That's going to be 2x minus x cubed over 3 minus x squared over 2 from -1 to 2. And if you do that correctly, you should get the area. Actually, we'll just do it really quickly just so we get an answer here. So it's going to be 4. Let's see if I made another mistake. Am I making another mistake here?
Mr. E, wouldn't it be 2 minus x squared and then plus x because...
You are correct, yes. Geez, what is wrong with me today? All right. I know it is. I'm thinking about the Super Bowl. That's what it is. I'm distracted. No, just kidding. I don't know why I'm off today. Yes, thank you. It's minus -x. Thank you, Emily. So it should be plus x. So it's plus x squared over 2. You know what? I trust you guys can get this answer. Let's not worry about getting it. Just use a calculator at that point. I trust you guys can do that, so we'll move forward. Any questions? Nope, okay. So summarize the steps. I'll do this as a text box, might be a little easier. Put it right here. Sketch graphs. And label curves with equations. Shade area. I know you can't see what I'm typing right now. You'll see in a sec. If necessary, find points of intersection. Using some algebra. 3. Is f of x greater than or equal or greater than g of x on your interval from a to b? If yes to number 4, then okay. Let me write this out here. Okay, here we go. So that's summarizing what we just did. Sketch the graphs, label them, and then shade the area. If necessary, find the points of intersection. If they say find the area between the two curves, they don't tell you like in between what 2x values, then they're wanting you to find the points of intersection. Use some algebra for that, like where you set the equations equal to each other and solve for x. Guarantee that one of the equations is always above the other one on the interval. And if so, then you have the liberty of just going with that integral. The integral of a to b of fx minus g of x dx equals area between the two curves. Now we are going to encounter situations when one function is higher than the other one is higher. We're going to talk about that in just a little bit. But let's keep moving here. Now you could use your graphing calculator to kind of help you out. And actually, the more I think about it, I should probably go into my other device here. Get 2 cosecs. Yeah, because I'm going to show you how you can do this more accurately. Let me just drop this down really quickly here. 2 cosecs y equals x squared minus 1. Okay. All right, so I'm going to pull up Zoom on my other device, because that's where I have the calculator. Sign in. Testing. Oh, hold on. Testing. Okay. Let's do this. Okay, you guys can hear me here? Good, okay. So let me pull up, okay, so now I'm sharing this screen here, and I think it's still recorded, which is good. Let me pull up the TI Smart View. Okay, so we go to y equals. Let's go and clear that. And I remember our equations were 2 cos x. Nope. 2 cos x and x squared minus 1. Make sure you're in the right mode, radian mode. And I'll graph in the Z trig window, option 7. There's cosine, there's that. So I want those points of intersection, right? How do I find those points of intersection? Hit second trace, remember it's all recorded, so you can watch again if you need to. Hit intersect, and put it close to one of those points of intersection. Hit enter, hit enter, hit enter again. So it gives us negative 1.265424. Now what I'll do is I'll clear and go out to the home screen. If you hit X, it gives you that value. I'm going to store that as alpha A. That way I get an exact answer. Let's go back and do it again. So go back to graph, second trace, option 5, move your cursor now to the other point of intersection, get close to, you're on the first curve, so that's why it's in blue. Hit enter, you're on the second curve, that's why it's in red. Hit enter again, you get 1.2654, whatever. So quit out, or hit clear. Hit X, notice it'll give me that. So now I hit store, alpha B. Now I'm going to integrate this. Remember the top curve was the cosine curve, the blue. The red curve was the bottom curve. Kind of reverse what I've been doing in my notes, but that's okay. So I'm going to do, again, cosine's the top curve. That's y1. So now what I could do is, oh my goodness, 2 cos x. That's okay, we're fine.
working. Now, what I'm going to do is I'm going to do alpha window, option 4, alpha A, alpha B. See, by doing this, you're going to get a more precise answer. Because if you round those limits too soon, you're actually going to be a little bit off. And what's going to happen is that when you do this test, I'll tell you right now, I know how I'm going to do this. I'm going to give you a problem, so find the error between two curves and type in your answer around the 3 decimal places. If you're off a little bit, it's going to say you're wrong. Of course, I'll look at your work. I'll give you the credit, don't worry. But on the AP exam, they want to 3 decimal places. And so if you don't have it precise, you will miss the point. So that's why I suggest you do it this way. And now we know they're going to have some person on May 4th on paper. We're going to have that option. I'm pretty sure that's how we're going to. But I think you'll have the flexibility. If you want to do it May 21st or later, you want to do it at home, I think we'll have that option if you want that. But now we know that, there is going to be a traditional version of this exam. Hit alpha trace to call up y1 minus alpha trace to call up y2. And then you do dx. Because it's the answer. So the answer is 4.995. Now, what if you didn't follow this level of precision and you rounded too soon? What if you put like negative 1.27 and positive 1.27? And then, of course, alpha trace y1 minus alpha trace y2. And then dx. Actually, we would have been okay. Okay, so I guess you would have been fine, but let's repeat that one more time. What if you did like negative 1.3? Some people will be even sloppier. And 1.3. Now you get a different answer, and that would be incorrect. But apparently, I guess if you had the 2 decimal places, that would have been precise enough, supposedly. But still, want to be careful. So that's how you can do that with precisions. You store the points of intersection as A and B. And to store it again, you graph it. You find the points of intersection by doing option 5. And once you get the points of intersection, you immediately go to the home screen, type in X, see what they say for X, and you store it as a letter by hitting store right above the on button, and alpha, and then all the letters you can see are in the top right corner for various buttons on the calculator. So that's how you can store stuff. Very useful technique and process. So I'm glad we had a chance to do that calculator demo. So let's go back to notes. Okay, so let me stop sharing here. And let me turn off this. Okay, now I'm back on my other device, which is good. Let me minimize that. Actually, I can just kick myself out of here. Okay. All right. Let's go back to sharing again. Okay, we're still recording. So now we know, and the steps are all laid out here anyway. So again, what did I just do? Add these 2 curves here, right? Remember I had cosine, which was done in blue on the calculator. It's kind of like that. I had a parabola with a vertical shift with 1 down, that was like that. And I had these points of intersection that I had to figure out, and I had to get the area between the 2 curves. And I just used the calculator to do that for me. And the answer we got was 4.995. So not too bad, right? I think you guys understand how to do that now. Remember, I'm integrating from A to B of y1 minus y2 dx, where this was y1, that was y2,
A was the x coordinate there. B was the x coordinate here. And we're okay. All right. Now, let's take a look at some things that are a little bit more complex. Find the area of the region R in the first quadrant that's bounded by y equals root x and below by the x-axis and the line y equals x minus 2. So what this is asking us to do is actually find us this region. We're being asked to find that. And I did say here in this, we could do this actually 3 ways. So let's talk about one way. One way is you can actually partition this into 2 regions. I'll call this region 1. I'll call this region 2. For region 1, what are you integrating? Well, it looks like that's happening at 2. So you're integrating root x dx from 0 to 2. And you can just see that because that's where the line touches the x-axis. Then region 2 is the area between 2 curves. Looks like it goes from 2 to 4. Yeah, because root 4 is 2. And if you put 4 in here, y does equal 2 as well. In fact, you could even just set them equal to each other. And graph in the calculator so or do the algebraic if you want. But anyway, it's going from 2 to 4. Top curve is root x minus parentheses x minus 2. And then you just use your calculator, work it out. I'm cool if you use a calculator at this point. Region 1, I think it's going to equal 1.88 something, I think. Region 2, I think it's like 1.44 something. Combined, I think we get about 3.333 repeating. It's actually 10/3, the exact answer. There's an exact answer you could get. Remember, the calculator, when it does the integration, it's actually getting you an approximation when it does this. Okay, so that's one way you could do it. Just partition it, integrate each of them separately, punch in the calculator, add the 2 areas. So that's pretty straightforward. You do it that way if you like. Another way is you can get a little bit cunning here. What if, so remember our region looked like this, right? We have y equals root x. Kind of looks like a shark. So if you so desire, you could have done this. And if you subtract those 2 areas from each other, what are you stuck with? This minus this just gets you just that. So you could do that if you want, if you think about that. And the way that would look is you would simply do the integral from 0 to 4 of root x minus x minus 2 times dx, and then subtract by the area of this triangle. The area of that triangle, I think, is 4, no 2. So you could do that, and that would work also. You would still get the answer. I mean, if I have my graphic calculator right here, I don't want to go back to my other device, but if I were to integrate that alpha window, option 4 from 0 to 4 of root x minus x minus 2 dx, and then minus 2, yeah, I do get 3.33 if I do this correctly. So it'll be minus 2, and that's 5.333. So I get 3.333 repeating. So that's another way you could do it too, if you wanted to. The area between two curves. And then that little sliver, which you know is the right triangle. The third method, which is what I think is going to be the most efficient, it's a little weird, but it's going to help us with page 5. And it might be a good time to actually do a break right now, because it's a little mind-bending. I think we do need a little bit of break from screen time. So let's do a 10-minute break. We'll come back. I'll finish off these notes. Then I'll give you a chance to guys do a little practice at the end of the class. So we'll do a 10-minute break right now.